Thank you. My name is Michal Polic. I'm a researcher of Czech Technical University. It's my pleasure to introduce the next session and the next invited speaker. The next invited speaker is full professor of robotics, mechatronics, and computer vision at Democritus University of Greece. He is the Dean of School of Engineering. He is director of the Laboratory of Robotics and Automation. He has been principal investigator of several projects funded by European Commission and European Space Agency. He supervised more than 60 master theses, supervised and co-supervised about 50 PhD theses, and now supervising about 12. According to the scholar, he has about 300 in peer-reviewed papers in journals and top conferences with over 6,700 citation. Please welcome Adonios Gasteratos.
Thank you for the introduction. And thank you for the invitation once again. I'm very pleased to be with you today. I'm going to present you human presence modeling and social navigation for an assistive robotic solution for detection of falls and elderly support. Firstly, let me introduce my lab at Democritus University. We call it Griffon Lab. It is this is our symbol. It's our location in Xanthi is very close to ancient Abdera, where Democritus, the philosopher Democritus, was born and lived, and our university is named after. So this is actually the emblem of Abdera. This is from an ancient coin of that area, and when I started back the lab some 20 years ago, I found it a nice emblem for a robotics lab. The Griffin. In the last 20 years, over 20 years that I started the lab, now we are 8 PhD holders and 15 PhD candidates. We have several running projects and past projects, mostly in the areas of autonomous robot navigation, human-robot interaction. A recent activity that we have undertaken is robotic manipulation and control, and as well as the industrial automation and machine vision for industrial automation. Today, having studied a little bit the SoRAIM and the Spring, the hosting project, what it is about, I have chosen to present you the results of a project named ASPIDA, which stands for Study, Design, Development and Implementation of a Holistic System for Upgrading the Quality of Life and Activities of Seniors. It is not apparent, but it is the Greek translation produces the acronym ASPIDA, which is a nice choice because literally means shield in Greek, and it was a national project to promote research in the universities and the research institutes at the regional level, and therefore we have made this proposal for to address the problem of aging population. And indeed, it is a very sharp social problem, and there are no easy solutions to that, owing to the fact that the life expectancy, the birth deficit, and the aging increase, they result to major problems, because we don't have so many, let's say, hands to take care of the elderly, that they increase more and more nowadays. And especially in Greece, we have this problem even sharper, owing to the fact that we are the second most aged country after Italy in the European Union. The main objective of ASPIDA is how we will manage to adequately care for our fellow human beings who are aging, by offering a holistic system to upgrade their quality of life and activities. And to that end, we have developed in the university, I mean, owing to the previous reasons that I mentioned, and the scope of the project was funded and with a very high score, and we have developed several technologies, part of which was robotic solutions, and that were conducted by my team. So the main objectives are autonomous living, improving the quality of life, reduction of hospitalization costs, commercial retirement system production, decongestion of and strengthening of health services, and reduction of mortality from falls. I will stay closely to the sixth one, because we were very close to address this issue, and we have produced many results on that. So, as I said, the consortium was only consists of several labs within our university in 3 different departments: the departments of electrical and computer engineering, the department of production and management engineering, which I come from, and all these are within the faculty of engineering, plus the department of physical education and sports science, that they took some measurements together with us on elderly people. So, in this context, we have evolved several activities revolving around the scope and the objectives of the project, including visual measurements for elderly, kinesiology assessment, rehabilitation of the elderly, infrastructure development, specialized robotic assistance. I will be more specific for this part because it was our part, and user-friendly development of user-friendly interfaces. And within the context of the project, we have made laboratory measurement both at the OCCEs and in our university. OCCEs are some centers, stands for Open Care Centers for Elderly, and they are some centers that are normally in every municipality, one at least or more, and they gather elderly people to pass their time or to exchange knowledge. And so we were in close collaboration with them, and we conducted several measurements and took several data sets either there or in the university. We have developed innovative robotics technologies, a kinesiology assessment tool, and optimal decision-making reaction in smart home environments, things that were done from other laboratories. In a nutshell, we have worked 25 professors, 20 postdocs, 39 PhD students, 13 laboratories, and we have worked with over 300 seniors located in 5 OCCEs, and we produced several deliverables and publications, more than 70s, that and some of them are still coming out, owing to the fact that the project was concluded only a few months ago. Let me first give you some overview of the laboratory measurements that we have conducted. We have conducted training of researchers in field measurements, fitness tests and interviews, biomechanical analysis of movement through the Vicon system, that it is installed at the physical education department, myoskeletal modeling through OpenSim, and code generation and algorithms in Python. And also measurement tools and data analysis through transition and cross-cultural adoption of questionnaires, pilot measurements and field tests and interviews, algorithms for data analysis, analysis of self-report accelerometric data, creating protocols, laboratory pilot measurements, and analysis of data of laboratory measurements at the elderly centers. Some of the results are briefly presented here, including posters and brochures. Very important, a fall prevention guide that we spread to the elderly people, and individual results from accelerometers and recommendations. In the elderly centers, we have conducted measurements through accelerometers on the vest of the elderly people, field tests, anthropometrically tests, and also we hand out questionnaires. These are the 5 centers that are located near our university that participated in this test, while many subjects came to the university where we have this infrastructure, and we recorded their movement and the forces and the muscles activity in several scenarios, like walking, static balance on each leg, reactive balance with increasing weight, change of direction while walking, and starting and sitting on a chair. And we produced also data sets out of that, and also made some publications that I'm going to present you later. Here is an example of these measurements and how it is captured in Vicon. We used some pointers, and the Vicon can locate the joints that each of these pointers is with very high precision and accuracy. And so we used it, all this data to produce the results and to in this and produce the data set. Okay, next slide. And in this part, I'm going to present you the part that of the project that was undertaken mostly by my team. Firstly, I want to share with you some knowledge that is practical, and when you move forward to your career, if you choose the academia, bear in mind that when you start a new project, you have not only the joy of research that you currently enjoy, but you have to go through a lot of administrative and financial burden. This is to say that we have studied at the beginning, given also the user requirements that we have discussed with the centers, elderly centers, and we reviewed several robotics assistants like the Eugene or the Hobbit and other robotics assistants that we wanted to purchase. And next we issue a tender. We discussed with the company if they could build a robot like the one that we wanted. We issue a tender, and well, things are not always going the way that are planned. So there were no bid the first time. The second time there were some issues with the papers. So we after about 20 months, we decided that we would buy different modules and build the robot ourselves, because otherwise it wouldn't we wouldn't purchase a robot ever. What we wanted with the robot to do was to have a human-aware robot navigation, energy efficient robotic manipulation, and the human body pose estimation through vision. Originally, our plan was to help the elderly people by means of 2 hands to get dressed, to help them with their shirt and assist them to, which is a quite difficult task and requires robotic manipulation in order to be more to the point we have chosen the energy efficient one, and also to this thing here to address the falls. I will explain later. So, as I said, owing to the fact that we didn't succeeded in purchasing the robot that we targeted for, we bought a platform, a tower, and one hand, because it was we were limited to budget. We couldn't buy the second one. Therefore, we forgot about our initial plan. And of course, a LiDAR and RGB and stereo cameras to help with navigation on the one hand, and also to locate people that are around and probably fall. We integrated all this through ROS, and we implemented, for the purpose of the project, this simple algorithm for fall assistance, as I said. So we use the robot to make the global map, then through localization and human detection. If we tracked some human fall, then through path planning and obstacle avoidance and local math update, we were reaching the human to be helped probably at that stage we would provide probably make an emergency call or something. So about the global map, so we used the standard ROS with the LiDAR. We use some standard algorithms for the global mapping. So the robot firstly builds the map. You see there are some holes in the map, so the robot has to move around the obstacle in order to build a more concrete map. So this is the first step for any robotic assistance to start the mapping. So the next thing was the localization. Okay, once the map is built, the robot should be able to localize itself in the map, and of course move around freely. So the robot knows precisely its position and can safely execute any future navigation or obstacle avoidance scenario. The next step is the obstacle avoidance module, where the robot assistance models the obstacles of the global map and adjusts the safety distance from the obstacles. And of course, the fall assist emergency algorithm, in which case the robotic assistants observe the environment and locates people moving in the space through the RGB camera, and also estimates the position of the moving people in real time. So in order, when a fall like here is detected, the robot approaches the person and in order to support him, as I said, perhaps to make an emergency call or to transmit photos of the incident to the doctor or to the carer, etc. Okay. Now, about the human aware navigation scenario, I think the previous talk was very informative about what social navigation is. We attempted an implementation here that was based in some of our previous work, where the humans are modeled with a Gaussian, a 3D Gaussian around, and they are considered as dynamic obstacles. So the robot actually performs navigation in this area. So, according to the description of work, that was the deliverable that we had. So we deployed algorithms to work in real time and promote independence and safety in ambient assisted living scenarios, provide a realistic action plan for emergency case of human fall, and provide the full open source implementation code that we have put it on GitHub. So although the project is already concluded, we, as part of future work, aim to the incorporation of additional data analysis and machine learning models, and potentially to further refine fall detection and increase robustness in more severe conditions like low lighting, multi-person fall, etc. Of course, apart these, let's say, conventional obligations that we have within the project, every time that some funding arrives at the lab, it is an opportunity for extra research to conduct. And here at this last part, I'm going to present you some advanced research outcomes out of this. The first one was energy efficient robotic manipulation. As I said, it was not written in our description of work, but we have chosen to go for it because it's a fancy and very modern research topic. And in the first part, we have developed our first attempt, because as I have said, we are a robotics vision lab, so we mostly do parts with navigation and recognition, and not that much control. So this is our first attempt to enter the arm control through energy efficient solution. So what we did was that we employed a spiking neural network, and we have trained it through Gazebo on a robot that was done as during the time that we were expecting to buy our new robot with an existing robot in the lab. So we have prepared the model and trained it in this scenario, and that work was published in a conference. The next one, after the previous work, this one followed. That actually we used an actor critic reinforcement learning algorithm, and the actor was the spiking neural network that explored the first 3 degrees of freedom, and the critic is a deep neural network that penalizing and rewarding the actor based on the results of each episode. And after the training position, the training procedure. The critic was left out, and we remained with a spiking neural network that it was an energy efficient solution. And we conducted experiments both in the 2D and the 6D case of our existing robot. This work has been published in Robotics and Automation Letters and also presented in the last IROS conference. And the video, actually, this video is from the IROS presentation. Okay. Here is another video. After that, we have purchased the robot. We applied the algorithm on the UR arm that is here, and you can see that the algorithm is performing well. And it reaches the goal and grasps the object. Okay. And the last work concerns skeleton extraction of elderly activity recognition through vision. So for skeleton extraction, there are several methods like wearable sensors, sophisticated ambient sensors, and interconnected devices. We instead try to perform such one using vision, and to make a complete bio-inspired ambient, a low-cost action recognition system using non-intrusive means like an RGB camera, because the other methods that I mentioned, people are complaining many times. Though, on the other hand, the camera is always, if the subject agrees to be monitored by a camera, it's not, there is no other nonsense that might produce. Training on time series data extracted from the RGB camera, providing valuable insights into their capabilities to handle human data. The investigation of effectiveness of energy efficient HTM, hierarchical temporal memory, and SNN, the spiking neural network architectures that accurately recognize and classify actions, and the illustration of competitive analysis between the bio-inspired networks and the base SVM approach that, as I will show you, prove that the proposed bio-inspired solutions are provide very accurate and very high-end results. So we have made a custom data set of 8 elderly individuals in several daily tasks, particularly 5 actions that have been recorded with an RGB camera and have been processed with the MMPose to get the 3D position of the joints. The actions is drink. At this scenario, the individual walks through the room. At the end of the room, it takes a glass of water and drinks. Gate, which is simply go, a simple forward go. Turn left. At the end of the gate, the subject makes a sharp turn to the left and similarly to the right. And the last one is that at the end of the corridor, there is a chair, and so the subject sits and stands again. This is an example of the action of drinking. Okay. So how did we proceed with that? We took the RGB video stream, capturing these 5 different action scenarios by all the subjects. We produced the MMPose model to extract the skeleton in 3D. And the output of the pose extraction subsystem was a skeleton of this dimension, and we processed the frames, and we created some time series to proceed with. And owing to the fact that the subjects have different gates, they have different times, they executed also the 5 scenarios in different times, and the videos were not equal. So we normalized them and to avoid aliasing, we cut them to the shortest one. So in order to recognize these actions, we performed first. We employed firstly an HTM. For those that are not familiar, it's a network that is issued by Numenta and resembles the neocortex functionality, and is based on Hebbian learning. It's a pyramidal architecture that every second layer there is at each layer there is an aggregator and a pooler, and that way it passes the information from a big input up to one single node at the top of the pyramid. We used 2 hidden layers consisting of sparse weight format followed by linear transformation. The k-winner layer is then applied to select the k top winners based on their activation, and in the output layer, the maps we map the hidden layers of activation to the desired output. The other solution to recognize the action was a spiking neural network. We used external libraries like TensorFlow or Keras, and the architecture that we used consists of input layer with output size 51 by 20, followed by hidden and output layer. The hidden layer is a single dense layer followed by the activation function utilizing leaky, integrate, and fire neural model, and the input data is fed to the dense layer, which serves as feature extraction, and the output layer comprises a dense layer with 5 units. And as a basis to compare with, we used the standard SVM approach. So here are the results in this table. You see that the HTM exhibits very good results, except that it has one missing. The SNN exhibits excellent results, while the SVM, in the SVM there are some cases that are not well identified, and the overall evaluation shows that the HTM excels, but and both in performance and time efficiency. And here is a confusion matrix showing all three cases that we used. So to conclude with this method, we provide an end-to-end ambient solution for elderly to recognize action from RGB data. And both the two bio-inspired networks, namely the HTM and the SNN, are very good for recognizing such actions. In terms of time efficiency, the HTM outperformed, but of course the SNN is better in terms of efficiency in power. Okay, and I'm coming to the last slide. So the key takeaways are that robotics and computer vision showcases significant promises in advancing senior support and quality of life towards the goal of ambient assisting living. The integration of computer vision can lead to improved monitoring, assessment, and prediction of potential faults. Real-world case studies underline the practical benefit and learning from implementing robotics and computer vision in assisting living setups. Our recommendations are to engage more robotics and computer vision with seniors to understand the potential benefits and challenges of the specific needs, to explore partnership with technology providers and academia to stay abreast of the latest advancement in computer vision and robotics, and to continue. Our future outlook is to continue advancements in computer vision, machine learning, and related technology herald a new era of assisted living and elderly care quality. Integrated computer vision with other emerging technology can unlock further benefits in operational efficiency, and a collaborative approach between technology providers, regulatory bodies, the elderly centers, in our case in Greece, or any other similar thing in your country, can accelerate the journey towards improved systems. And with this, thank you for your attention. I want to attribute credits to my postdoc fellow Dr. Ioannis Kansizoglou for because he assisted me very much both with this research. He was the postdoc of my lab that participated in ASPIDA, and many of the slides were borrowed by him because it was part of the project review meeting that he very carefully prepared for. Thank you.
So thank you for the great presentation. Are there any questions? Okay, let's start.
Yes, Prof. Thank you very much for the talk. My question is that in the approach which you showed, uh, the approach is very much limited by the field of view of camera or the sensors on the robot. Is that true?
Yes, indeed. The integrated solution had in the integrated solution we have foreseen that there will be also cameras around in the room to observe the state of the elder. However, due to time limitations that we have had with the procurement of the robot, we had only the time to perform the tests in our lab settings, and we didn't move it to the smart home.
Okay.
So actually, your remark is to the point. But I don't have any videos or something to show because we didn't produce.
Okay. My connected question is that, yeah, I was thinking of infrastructure sensors, but if those sensors are connected to internet, there are privacy concerns because of the loopholes in the hardware or softwares. So wouldn't it be better that we put wearable sensors on patients and try to trigger the fall detection from there?
It's also there is also a privacy violation also on that. Any measurement that can be taken, it's not only the face that matters. As soon as the subject agrees that measurements can be taken by either camera or any IoT device, because if you have a belt with the accelerometers on your vest, on your waist, these are not anonymized.
Okay.
The measurements, you know, that are taken from Adonis or from Xavier or anybody. So the subject has to agree that also these kind of measurements should be available to the therapist, to the hospital, and in general to be monitored. So I don't see how the problem of privacy
is not resolved.
is
but
solved.
Definitely it solves the problem of field of view issue. We don't
Yes, but if you have installed cameras all around in the four corners, plus the one on the robot, you have full
information. Okay.
And moreover, there are in other laboratories worked with the cameras in the smart house, and there were other laboratories working with accelerometers as well.
Okay.
We didn't omit any solution. What I presented here was the job done by my lab. Actually.
Okay. Well, just one last question. I know it's not related, but I would like to know your view. Rather than detecting the fall, it will be much better to predict the fall with a wearable sensor. What are your thoughts on that, Prof? Thank you.
Actually, it is a very good observation, and indeed, it provides you a few seconds only of that. Imagine that your grandfather is moving, okay, and he's about to fall. What could the robot do at that moment? Even if he would predict that he's going to fall in the next 2 seconds, it's not much time to do something. If I yeah. I'm not sure I got the.
I'm saying that, yeah, a long prediction will be a very hard challenge. Yeah, that is not possible. But even if we are able to predict it 2 or 3 seconds before, we can avoid hazardous collision to pointy objects or something like that. does it, like if I am about to fall, I will not,
Yes.
my sensor will trigger, and at least I can choose to fall in some.
What would be the actuation to assist you towards the
From that
the
wearable
prevention?
sensor.
What would be the actuation of?
From that wearable sensor, maybe a vibration or something.
I don't think that an elder people, if it has something vibrating while is about to fall, can do much. I'm not. I'm not sure.
There are so I've seen already some sort of solutions that are actually when someone is about to fall, then they trigger some sort of airbag, right? That's something that is mounted on the person, right? So that is one thing, but it's not like the time the robot takes to get there. I mean, the person is already in the floor. 3 seconds is like it's super short for a robot to do something. It has to be a specialized device, I think.
So the only thing it can do is to ask for help and send some photos of the status. Yes.
I don't have much experience with elderly people, but for babies and all, at least, if you know something's like they're gonna fall or whatever, so, sometimes you put like an obstacle or something so they don't fall like in their sleep or those kinds of things. So maybe like the bed could have some things which you're like, oh, if this person is turning too much, then, you just kind of raise some, I don't know, like, I'm not really able to express, but yeah, there are like airbags also, and there are some other solutions, but like the point is that it should not be that the robot should be able to move from across the room to help. It's more like in the surroundings, like wherever the person is, maybe we can put in place some mechanisms like he said, and like focusing more on local stuff which can do some actuation, some action. Yeah.
Okay, I have been involved both with babies. My children are already
sure. No, I
10
get
and
it, yeah.
more, and also with elderly because my my parents are already over 80s. I can assure you that they are totally different cases. The elder has an opinion, and it has a very strong opinion.
Thank you for this perspective. Yeah.
You cannot convince him. If it is to put an airbag on him, you have to convince him that it is for his own good. And I'm not sure that 1 out of 10 might put such a device on it. And it requires also training that they are not that open to training. I have gone through this experience the last 5-10 years, and believe me, they are very stubborn, and we will become very stubborn at their age. We have to think with their mentality and to provide solutions that are good for them and that they can accept it. So yes, but it's out of my discipline, out of my field. Perhaps Vicky, that was here the other day, would be more appropriate to say how to treat.
No, I agree, and it's a fair point. I think it should be more tailor-made to what they consent with, what they actually need, because even people who use walkers, sometimes they forget they're supposed to use a walker and then they fall. I've seen those cases a couple of times in my own life. So yeah, it's like, we'll have to think about a lot of scenarios in detail and work on it. Thank you.
Okay, thank you for this question.
Yeah, I just want to add to your point also, like as an example, my grandma, she refuses to wear her hearing machines because she just doesn't like how it looks on her. So that's the thing. So I think that's the big thing. But also I wanted to add, like, maybe the complex solution would be, as you told, like design the space to be safe enough. So if somebody falls or if somebody has trouble, the space is designed the way that it will be safe, and the robot could really do a good thing even if it predicts the fall or just detects it. it can just immediately call for help, and it will save so much time. So I think the complex solution would be that the environment and the robot cooperate together in order to provide safe spaces.
I wouldn't agree more than that. And also the training is very important. I mean, that's why we collected questionnaires to know their opinion, and in our team there were also a psychologist to design solutions that fit their needs. This is of utmost importance.
Okay, there is time for the last question. Is there some? Okay, I would have a question, more technical one. If you look at the actuators which are power efficient, you have mentioned that there is some network which is trying to do the actions, and then there is some criticism network who is giving the reward, and it's also a deep network. So if we have directly what we want to do with the actuator, we don't need the second network. So the question is, how do we learn the criticism network? Because actually we just move the problem from having labels for the actuator to have the labels for the criticism network.
Well, in our first work, we did only that. But the previous slide that I saw, but the space is enormous, is vast, and what the reinforcement based network does is to make this vast space smaller and to train the SNN more efficiently. Instead of going directly to to try to train it with all the possibilities that can take, which might not be able to find a solution after all. I mean, this was the idea. Yes.
Okay, thank you once again for great presentation. Okay, and now I will present what was done in the scope of Spring in the work package 2. The work package 2 has an objective which is quite complex, to develop models, representation, and algorithms for building and upgrading environment map with semantics, annotations to support data simulation and robot self-localization. If you are not sure what does it mean, I will go to outcomes which are more clear. The outcomes are the audio-visual data simulator, robust localization from images, tracking the robot pose in real time, and building the scene representation for localization and mapping, so that we can understand the environment surrounding the object. I will focus most on this robust localization and tracking of the robot, because this is what is currently running in RA. However, I will give a brief overview of all the tasks. So the task would be, if I split it to 5 tasks, it would be simulation, localization, tracking of the robot in real time, mapping of the surrounding environment, and understanding of the environment. At the time the project was beginning, or during the project, we had several restrictions. For example, we cannot record any patient in the hospital. Also, there was a COVID, and also there was a need for having ground truth camera poses. So we needed to somehow take the capture of the environment and do the simulation instead of running all the experiments there. For that, we do the scans by Matterport scanner and create such an panoramic RGBD scans and also the mesh of the environment of the one floor of the hospital and the living lab. This data was used to run the simulation in AI habitat where the robot can move in that environment. Like naturally, we can add any cameras which he has and sensors, etc., and run, for example, navigation in it. Moreover, you can see that this is running based on top of the mesh, which was scanned. So it's not high quality. So having higher quality, we also extracted the cutouts out of the panoramic images and run do a like simulation codes for having crowded spaces, so we can evaluate how well our algorithms run in dynamic environments. Okay. So if I look at the localization task, it can be split to the dense and sparse localization. Both of them are like using the same block, which is called image retrieval. The localization is actually the process of finding the initial pose of the robot in a large-scale environment. So if you have large-scale environment, you need to first get something which is like similar looking images. That's the task of image retrieval. And then based on the similar looking images, you can find better or more accurate pose by either this dense or sparse approach. First, I will tell something about the dense approach. It actually does several steps. First, we get a query image, and we have map represented by an images with known pose and the mesh of the environment. Having so, we will do the image retrieval, which will find similar images in the map. You will play with this and in the hands-on session. Then there is sparse verification block, which will take these similar images and find the matches, verify them, and somehow extract the pose for each image which was retrieved, like with respect to each image which was retrieved. So it finds the pose relative to this image. And then there is the dense verification. This dense verification is done by rendering an image out of the estimated pose using the mesh of the environment. So having so, we can compare the rendered image with the rendered image, which are, for example, here for the inloc, with the query image, which are captured in here. And we did so by using the rendering from the simulator, which was printed before, retrieved 100 images, do the verification on 10 images, and rendered that 10 images. Having this approach, you can see the blue dots. The blue dots are the scans or the images in the map, and the green one are the poses which were localized within 25 centimeters. Yellow one are few poses which are between 25 centimeters and 1 meter, and the red ones are the poses which were localized with error larger than 1 meter. So this approach somehow worked. We started with this, however, it's slow. Yeah, because of the rendering, which is here, not here. And also can be improved. I will just briefly mention we also improved this approach about like semantic localization. So we also rendered the semantic masks and compare them by with the semantic masks to adjust the score and select better the good pose at the end. However, as I mentioned, it's slow. It runs tens of seconds. So what we can do about that is sparse localization. It's another approach. This sparse localization has to build the map before running the experiment. It's actually composed of the classical structure from motion. It will you can see, for example, these input images, which were aligned, let's say, reconstructed by the call map with some tweaks, so removing the similar images, etc. And we got something like this. So we have sparse point cloud around aligned cameras. And at the time of the inference, and also one more thing, we have pre-computed the feature vector for each image, which is the part of the image retrieval. So at the inference time, we have a query image. We will extract a feature vector which describe the image. Then we do the cosine similarity, so just multiply these vectors in the database and this one, and select which images are similar. That's the image retrieval. For that, we use some SENet, which is one of the latest image retrieval approach. Then, having similar images, we have some images here, for example. So we find 2D matches between the query image and database images, which were retrieved, and find, therefore, also the 2D, 3D matches, because for the database images, we have this 2D, 3D correspondences. So if we have 2D, 2D correspondences, we have also 2D, 3D correspondences. And that's the classical approach, absolute pose estimation, where we estimate the camera out of the 2D, 3D matches. So that's more or less standard. We just improve the image retrieval step. And further, to improve the quality of the localization, we use the multi-view approach, which will take, for example, the forward-facing and backward-facing camera, and find for each image 2D, 3D correspondences. Then, if we know the relative transformation between these two images, we can compute the generalized absolute pose solver, generalized absolute pose problem, so we can get a pose of the set of images, not only one. And here you can see how accurate it is. If you use single image, for example, something like 38% of localization queries were localized within 2 centimeters, while if we take like 2 images, the front facing and backward facing, we have something like 73% of images localized within this threshold. So there is large increase, especially for the having single or 2 images or 4 images. There is large step increasing the quality of the localization. So that's what is running in ARE. Now, having the initial pose, this takes about, I don't know, 1.5 to 2 seconds to get it. Yeah. So, but we don't need to pose each 2 seconds, so we need to track the camera all the time as the robot is moving. And for that, we have some SLAM method, or SLAM, and RTAP map representation. And that's what you already seen somehow in the in these demos. Here is an example of the mapping where the robot is moving through some environment, and getting by the SLAM and RTAP map the map of the environment. The same way we use the cameras, and the same way we reconstruct the the map for the localizer, align this map, and we have the same coordinate system for both maps. So then we can use directly the hierarchical localization as the initialization, and then track the pose of the robot in real time. So here's, for example, an example where the localization, where we have some initial pose. I don't know if you saw it. There was like running. Yes. Here, the yellow one is what we got from the H-log. Then this was used as the initial pose, and then we are tracking. So it just goes to the correct place, and that's used later on as for the tracking. Okay. No. This. And so, having the robot pose in the real environment, in the real time, we can focus on other tasks. For example, the mapping. The mapping is taking the map of the environment. For that, usually we know the camera calibration, so know what are the parameters of the camera. I will probably skip it. Then we have the sparse reconstruction. You already saw it. We can run some pipeline, which is doing the sparse point cloud and the camera poses line. And if you want to have like more detailed info about the three-dimensional space, we have to run the dense reconstruction. So I will skip this calibration. You can calibrate by many ways. We did it several ways. What is important, we published several papers to avoid this calibration, to estimate the radial distortion, for example, for the cameras directly from the images which are localized. And there is still work in this area. Regarding the dense mapping, again, there are like two main approaches. One is to use some classical multi-view stereo. This is the task where we use the patch match net. The thing is, you have several images, you have their poses, and you are finding the depth maps for each image. But you need the multiple images. This gives us something for the hospital environment, but it was not trained on the hospital environment, so it's not super accurate, and it would be better to retrain it for the domain-specific data. However, it's super hard to obtain enough of this data. So the second approach we tried, and which is particularly useful when someone is approaching the robot, or there can be collision or whatever, is to depth completion. It's if you have single image and you have the sparse correspondences, you complete the depth around the sparse correspondences. That's what Rakshit presented in his thesis, and we got something which is really not accurate enough for like nice dense reconstruction, but for example, estimating when someone is approaching the robot is enough. So there is still space for improvement about for the mapping phase. Now, last part is about scene understanding. So we can use either two-dimensional data, three-dimensional, or recently some mapping between text and images, etc. So that's and the large language models. So about two-dimensional data, we have YOLACT, which is two-dimensional segmentator, and we use it for segmenting the objects at the hospital. The problem is that there is a lot of objects which we don't have in the data set because the general data sets usually don't have the data from the hospital. So what to do with that? Focus on this problem, and if you know the pose of the robot, you can easily get it usually somehow selects the objects correctly, but do not assign correct label when you have unknown objects there. So you can, if you don't have consistent labels, you can somehow get these images of the object, and either put it into some latent space, which each image is a point, and measure somehow consistency if these points are related to single object and it is known, or use more advanced anomaly scores. It's called to get whether the object is known or unknown, and having the decision, this is unknown, we can put it into the training data for the classifier, 2D segmentation. The problem here is that having like 5 images is not enough to train this network. So we also use the MyGym generator to, if we are able to, and here is the step which is not fully done, if we are able to get like nice 3-dimensional reconstruction of this, we are able to very well train the segmentation of the new objects. But the weakest point here is from these images which are unknown to get the 3-dimensional model. That's now the state. So let's continue. What if we are not able to directly train this object, and we know that it is unknown? What we can do, what we tried, is to put it to the large language model. What it will tell us. So, for example, here is the experimentation where we put these images, these cutouts, or the original images to mini GPT-4 and Lava, and by some human evaluator evaluate what's the accuracy of the responses. So, yeah, it's about 70% where the responses are accurate. If you have time, I can go to some examples during the questions. If you move from 2D to 3D, we tried the Minkowski engine to segment the space, the semantic classes. However, this works really well. You can see this on the Broca data, on the hospital data set. When the point cloud is nice, when the point cloud does not have large holes, a lot of noise, etc. So here still, it's a problem to get a nice 3-dimensional point cloud of the space. But if we have it from the laser scan, it works. And the last approach, and I will finish, is quite recent and interesting. Just a few months ago, there was the first paper about mapping between clip feature vector, which is actually trained on large set of images and captures like the text to the image on the internet, and we can distill the mapping between the image and the clip feature vector, actually between the text and the image to individual pixels. If we have it, we can train 3-dimensional mapping from the surrounding space to this clip feature vector. And the benefit of this is that if you have any question like where can I sit, where can I don't know, exit this room, etc., it will create us the same feature vector. So the cosine similarity between this feature vector and this feature vector is high when this match. So then here is an example. For example, by the way, we tested 2 papers, the one which was not worked super well, and the second one which I will show you now. This is an example, and this is end of my talk. So you can see how, for example, LERF is able to segment based on the text query what are probably related places in the 3-dimensional point cloud or map. You know, if the prompt is general, we will get general area. If we get something like more specific thing, it will select specific places where, for example, posters are, where is the fire or something, an office, etc. So thank you for attention, and I will be happy to answer your questions.
Yeah, so I assume that in hospitals we have a problem with localization because many places look the same, because they are all white walls. So how do you deal with this issue? Do you also use GPS as an additional support, or do you just like wing it and hope it works?
There is like I did like global overview of the methods. There is a lot of work in individual like small blocks how to match the images. For example, few months ago there was a new algorithm for matching the images, which is glue stick code, and you also assume lines. So if there is nothing almost and you have just few lines, you are also able to match between the database and the query image. There is a lot of work in this direction. We did not use like GPS for in indoor spaces. It does not make sense. You can use GPS to select like the building, and then you have to use the image retrieval and the other steps. Yeah. So there is effort to not like only believe that it will work. Yeah, and we are like implementing them to make it better, especially for the like matching between image and the query image. Yeah.
Other questions for Michal? Yes.
Thank you. Thank you for the presentation. I really enjoy it. Quick question. So all these algorithms that you like show us to us are kind of quite heavy, right? And when I try to apply them in real robotics, it takes forever normally. Could you give us some recommendations, like to put these algorithms in robotics, or what are your insights on this? Like, you are doing it remotely on a GPU inside the robot, or could you give us some recommendations to apply all these things that you have shown us into robots?
Yeah, sure. I'm not sure where the RTAP map SLAM is running. I believe that RTAP map SLAM can run on the robot.
Yeah.
It's not super heavy, and that's the real-time tracking. So if you run the like some remote machine, the localization step, and then the tracking on the robot, it's quite okay because you will have like, you don't need to localize each 2 seconds. You can localize when you get lost. So you can run something which is running online on the robot, and just if you are lost, you will ask where I am to the server, and server give you the pose, and you can then track again the camera. So yeah, I believe that's, yeah, you need some server for the localization, but then it can run like in real time on the robot.
And then one question, maybe you mentioned that in the presentation, but I probably missed it. How do you know with Ari on this project that you are lost? Or what are the heuristics that you are using to know that, oh, I don't know?
Yeah, usually the SLAM gives you some score or some like value how accurate the localization is, and if you are localized, it's based on the number of matches it found, its tracks, and if it lost everything, you will get like no matches with the surrounding space. So you should get it from this information.
All right, cool, thank you.
Actually, we were lucky on Monday when we showed the demo because this didn't happen. But when it happens, then the robot is just stopping. I think the SLAM gives some feedback, like I'm lost, and then there is no. Any other question? I think another way to deal with this problem, if you're implementing this with a deep net, would be to look into quantization methods that would reduce the number of weights, the amount of memory that you need for the weights and for the activations. So that could also be or you put a larger GPU on your robot.
Yeah, there is always balance between the heaviness, but the computational power and the results. Yeah, if you have better GPU, you can use, for example, more key points, you can use better algorithm, which takes more VRAM, etc., etc. So it's always a balance between the accuracy and having it in real time. For example, the localization, the SLAM is running for real time.
Yeah, I think it's very important to understand what components need to run very fast on board and which ones. It doesn't matter if you get like a 500 milliseconds delayed answer. That's also an important thing to think about. All right, so if there are no more questions, let's thank Michal and Antonius once more.